Alright, so my topic is speech driven 3D emotional facial animation, and it's supervised by Dr. Mohsin. So, understanding relationship between how speech and the facial muscles move corresponding to speech is really important in understanding and analyzing human faces. So, for that end, we need a general and robust method that works for any person speaking in any language, corresponding to any face type, and we can convert it into a 3D facial motion. We also need generalization across unseen subjects because we just don't want it to work on the training data only. We want it to work it out in wild too. And it should work across variations in audio, like people speak with different speeds and accents, and there is noise, and then facial variations, different speaking styles, and different shapes in faces produce different motions of faces. So our reference paper is VOCA, which from the Captured Learning and Synthesis of 3D Speaking Styles paper. So VOCA takes speech signal as input, passes it through deep speech to get the character probabilities of English alphabets corresponding to that slice of speech signal, and then it passes that character probabilities to shaded convolutions. There are some dense layers, and then there is a decoder, and then the decoder out, and then there is a template mesh, which is basically 523 points in 3D space, vertices in 3D space, and it outputs 523 vertices in 3D space from this template mesh, and we add them both and we get the output. I'll explain everything in detail in future slides where I'll get into details of the architecture. So please be patient with that. So before that, we'll first go through the face model that VOCA is using, and which is Flame, which uses some scans of human heads to learn which are expressionless and are in the same pose, and it uses them to learn the shape space by applying PC on them, and then it combines it with the shape space with the jaw, neck, and eyeball motions by adding joints on the eyes, 3 joints, one on the eyes, one for the eyes, one for each of the eyes basically, and one for the jaw, and one for the neck. So they are controlled by those joints, these motions, and then the expression space is then learned by using a data set which is rich in some really extreme case emotions and great variation in emotions of 3D 4D face sequences of humans. So this way, safe space, expression space, and pose space are really disentangled, and we can control them separately by using shape, expression, and pose parameters. We don't need color space, when we'll see why later. So we'll now get into the speech recognition system of VOCA, which is deep speech. So as I told earlier, that it takes speech as input and outputs the probability of the English alphabets. For example, here the person is speaking C, so C has the highest probability, and AT cat, and then the inputs are the so in the feature extraction stage, it extracts the MFCC coefficients of mel frequency coefficients from that speech slice, and then it just passes it through a layer of ReLUs, 3 ReLU layers, and a LSTM layer, a ReLU layer, and a softmax at the end to just get the character probabilities at that timestamp. So we are gonna get back to VOCA again, and we are going to study the architecture in detail now. So input signal, so we first split the input signal into slices. So we are going to make 60 slices per second. I'm gonna call it 60 frames per second, just to make it easier to say. So per frame we calculate 16 time windows, 8 time windows before it and 8 time windows after it, of the same length, and basically we get total, so 8 before or 7 after, whatever, we get total 16 windows as input, centered around that timestamp. And we get, after passing to deep speech, we get 29 character probabilities, and then we add one hot subject encodings. We have 8 subjects, so dimension increases to 37, and then we pass it through a set of convolutions. So convolution is applied on the time axis, so it is applied on the window axis, which is basically the time axis, and it's a strided convolution, because the stride is not unit. So the purpose of applying it on the time axis and making it strided is to add temporal stability to the model, because otherwise it will because otherwise there will be no correlation in time between the speech signals if you don't add this. So there are 4 layers of time convolutions like this, and in the end we just add concatenate the identity information once again. So why are we adding the identity information? Because we can just use any, so different speakers in the training data has different speaking styles, so it is basically just to access different speaking styles from the training data. Alright, so afterward there are 2 fully connected layers, and the encoder network ends here. The encoder network's outputs has an output of size 50, and then there is a decoder network, which is basically just fully connected layers, fully connected layer, and it outputs 523 displacements in a 3-dimensional space from the template. We just add that to template and we get the output. So that's how VOCA works. So we are going to see how it the output.
Embedding using deep speech, a pre-trained model for automatic speech recognition. Then we used strided convolutions and a set of nonlinear transformations to learn.
You can see they are explaining their paper through by using VOCA itself. So that's a very cool thing. So how are we going to proceed with this? While VOCA generalizes well to the unseen subjects and also works on the languages it was not trained on, even though deep speech outputs probabilities in English, we'll see. I'll show examples later in my work how good it is. It still animates them in 0 pose, and the head is just in a single pose for all the 3D models generated, and there are no emotions on it, and also it doesn't account for upper face motions and like eye motion and eyelid movement, which really convey a lot of emotions. So we propose to incorporate facial motions which are as a result of speech and make it look more human like. So for that we are using DECA. DECA is the latest state of the art in converting input images into 3D models, corresponding 3D models with quite real looking textures, which so basically we really don't need the texture right now. We only need this part, so we are going to only use this encoder, which is outputting the identity, pose and expression coefficients corresponding to flame, and that's all we need from DECA for now. So yeah, we don't need the albedo and displacement maps as they are irrelevant for the facial motions. They are just there for making it look good, and we can add it later. It's not really important for the project. Alright, so we are using those flame parameters corresponding to each image we got from DECA, and we create custom templates for VOCA, and we gave an audio file of Qaeda to VOCA 2, and then this is the output.
आप आजाद हैं, आजाद रहें। आप लोग इस मुल्क पाकिस्तान में अपनी अपनी इबादत गाहों, मस्जिदों।
Alright, so as you can see, it works pretty well on Urdu language and on Kite's 3D model, which it is not trained on.
आप
So I used a dataset from Workspace, and it contains 12,000 images and the CSV file for emotion annotations. We scaled them as expected by Deca, and we used Deca to get the flame parameters corresponding to these 12,000 images, and we created a dataset class in PyTorch, and so basically we get flame parameters and corresponding emotion annotations, so which can be translated to 3D models using by easily passing those parameters to flame to reproduce those 3D models with high fidelity. So then I designed a conditional GAN to generate emotion specific flame parameters. So we pass a one hot vector of the emotions along with the noise vector to the GAN, and it should output it will generate flame parameters corresponding to that emotion, a random happy face or a random sad face, something like that. So the flame parameters are basically of 156 size and one dimensional, and there are 100 shape coefficients, 50 expression, and 6 pose coefficients in this that we have captured from the Workspace dataset. So they can really produce a really high quality flame 3D head model from just these amount of parameters. Flame can do that. So for emotions only, really expression parameters are important, because flame has really disentangled shape and pose from expressions really well. So we are going to generate only these 50 expression parameters from our conditional GAN. I'm still working on it, and just trying different hyperparameters and different GAN architectures to make it work better. So in future, what do we intend to do in future is that we are going to use existing state-of-the-art methods to get emotion annotations from the speech. So either we can do that or we can train our own model. Let's see whatever suits. So I found this IE mocap dataset, which contains 12 hours of audio visual data. It contains videos, also the corresponding speech separately, and even the motion capture of the face during the speaking, and then also the text transcriptions. And in addition to that, the videos are properly annotated along the time axis with the corresponding emotions of the speaker at that time. So it basically contains everything we need to convert those videos into their flame model mappings with annotated emotions. So our next step is to generate a dataset of flame parameters corresponding to these videos, and emotion annotations are already there. So we will use those flame parameters which have captured the emotion information, and then we are going to learn the corresponding flame. So in the end, our input will be an emotional audio and a template mesh, or really an image. We can use Deca to get the template mesh, and then our output will be a fully animated 3D face, which will also portray the emotions that are being conveyed in that speech. So that is our final goal. So thank you very much. If you have any questions, please feel free to ask.